Last week we considered an object that was falling due to its own weight and considered a linear drag model, which is appropriate for low Reynolds number environments. We kind of took the example of a grain of sand settling through water. Instead, today we're going to consider a nonlinear drag model, which is more appropriate for, say, a boulder falling through the sky. So we're going to take the same looking picture of an object, but consider it to be like some large human scale kind of boulder falling through the sky. So if we set up our Newton's second law sum of forces here, be summing, we'll take positive y down this time. Sum of forces would be our mg minus the force of drag, and that's equal to ma. But here we're saying the force of drag is proportional to velocity squared. So we'll use the same k coefficient. So it's equal to some coefficient k times v squared. So we can put that in there. So mg minus kv squared is equal to m. And a is just the derivative of velocity with respect to time, right? So here, if we take a look at what we have a differential equation that is, again, first order. So, this is just v dot. It's just first order, but it is now nonlinear because we have a velocity squared here. So this is a first order nonlinear equation. And we're going to solve it via a different method. This is a separable equation. So we're actually going to leave acceleration in terms of dv dt, and we're going to separate the dv and the dt. So we have m dv dt being equal to mg minus kv squared. What we want is all of the v terms to be on the same side. So we have a dv on the left, and we want that kv squared term on the left. So we'll just divide both sides here by what's on the right side. So we have m over mg minus kv squared, and that is times dv dt, and we're left with only 1 on the right side. And what we can do is we can move dt over to the other side, and we can move the m in the numerator over to the other side. So we have 1 over mg minus kv squared dv is equal to 1 over m dt. And finally, we can pull out a negative k in the denominator here. So minus k. So we have mg over k plus, or actually here, we have mg over k minus, let's see, we have v squared minus mg over k. That's what we have. All right, dv. And on the other side, 1 over m dt. And we can go ahead and bring that minus k over. So now we have 1 over v squared minus mg over k dv equals minus k over m dt. And what we can do is rewrite this in terms of this variable that I'm going to just choose to be a. So we can set a equal to the square root of mg over k. And we'll see later what the significance of that choice is. But for now, what that allows us to do is say that we have 1 over v squared minus a squared dv on the left and minus k over m dt on the right. All right, so we've separated our equation, and now we can integrate both sides. So we're going to integrate the left, and we're going to integrate the right to solve. And in fact, this minus k over m can come outside the integral, so we can even just kick it over there like this. And what we have on the left is a situation of partial fractions. So we have the integral of 1 over v plus a times v minus a. It's a difference of squares, dv. And on the right, minus k over m. And this, we can just evaluate kt over m, right? But on the left, we have this partial fractions thing. So we can evaluate it over here. Partial fractions. So 1 over this v plus a times v minus a. The way we do this is we set it equal to some a over v plus a and plus b over v minus a. So we're kind of trying to deconstruct into partial fractions, right? So therefore, if we multiply the denominator on the left side over onto the right side, you're left with 1 on the left side, and you're left with, so a over v plus a, and you're multiplying v plus a, v minus a, and the v plus a will cancel top and bottom. And then over here for the b, you have v minus a on the top, and you're multiplying that denominator. So v plus a, v minus a. And the v minus a's will cancel, so you're left with the v plus a. So you have 1 is equal to a times v minus a plus b times v plus a. Right? So if you consider setting v equal to a, so in the case where v is equal to a, if v is equal to a, then this term over there goes away, right? And you're left with b being equal to, so if v equals a, then this becomes, then this is a, so then you have 2a, and so b is equal to 1 over 2a, right? And if instead v is equal to negative a, then you find that big A. So if v is equal to negative a, then this term goes away, and this goes to negative a, so that becomes minus 2a, and so capital A here is minus 1 over 2a. So those are your terms that your values that you can plug in. Going back to our integral, what this does is we can write this as the sum of two different integrals. So we can say the a on top, right? So we have 1 over v plus a times v minus a dv, and that can be split up into the sum of two integrals, v plus a dv plus the integral of b over v minus a dv. And now we have the values for a and b. So really, this integral, which we're taking from the left side of our equation up above, we have minus 1 over 2a minus 1 over 2a, which we can put outside, minus 1 over 2a, 1 over v plus a dv, plus 1 over 2a integral of 1 over v minus a dv. And all that was equal to minus kt over m, minus kt over m, to recover our equation there. All right, so now the integral of these things is just the natural log, because you have something, you have 1 over something, right? So we have minus 1 over 2a ln of v plus a plus 1 over 2a times natural log of v minus a. And we have minus kt over m, and let's add our plus c term here since we've evaluated all of our integrals. So rule of natural logs is we can say that this is, so we can pull out a 1 over 2a here, and if we do that, then we get natural log of v minus a plus minus natural log of v plus a equals negative kt over m plus c. We can move that that 2a over if we want, and the subtraction of logs means that we can stack them. So natural log of v minus a over v plus a, right? And then we move that 2a from the denominator up, so minus 2a kt over m plus c, and we can just absorb it into the 2a into that constant there. No need to write 2ac, it's just a constant. So we can absorb that. And if we just take the e of both sides, if we raise e to the power of what's on each side, then we cancel out the log on the left, so we're left with v minus a over v plus a on the left, and we have it's going to be e, and then those are going to be combined via multiplication, because addition of natural logs is multiplication. So c times e to the negative 2a kt over m. All right, so what we really wanted was the velocity. So we can keep going with this, but what I see and I notice is that we're really just trying to dig out these v terms, and we're going to be doing just a couple steps of algebra, and we would have to rewrite all of this on the right over and over and over again for our few steps of algebra, which seems kind of unnecessary. So I'm just going to temporarily say gamma is equal to this whole junk on the right, c times e to the negative 2a k t over m. So therefore, just for a second here, we have v minus a over v plus a being equal to gamma. And that's nice because now we can go a little bit faster. So v minus a is equal to gamma times v plus a. So therefore, we're trying to get all the v's on one side, right? So v minus gamma v is equal to gamma a plus a. So then we can pull out a v on the left side, and that's 1 minus gamma is equal to, we can pull out an a and say 1 plus gamma. And so therefore, we get v, the velocity, as a function of time as a times 1 plus, I'm going to go ahead and plug in what this is now, c times e to the negative 2a kt over m divided by 1 minus c times e to the negative 2a kt over m. So instead of going and solving for that constant, we're just going to stop it there, but we're going to do our same terminal velocity evaluation here. So back up here with our free body diagram and our Newton's second law approach, terminal velocity means that mg is equal to the force of drag. And the force of drag is kv squared. So mg is equal to kv squared. So therefore, the velocity as the time goes to infinity for terminal velocity you divide the k over and you take the square root. So square root of mg over k. So we should see that if we take the limit of our equation that we arrived at as t goes to infinity, that we get the square root of mg over k, because that's when the forces of this quadratic drag has balanced that of the weight. So here, do a similar evaluation. Similar evaluation. So terminal velocity. So the limit as t goes to infinity of all of this junk, right, of a, which, well, we'll plug it in after, times 1 plus c e times raised to the negative 2a kt over m divided by 1 minus c e to the negative 2a kt over m. So these e to the powers, it's 1 over, right? So it's really like, in each case, c over e to the 2a kt over m. And so as t goes to infinity, this denominator will go to infinity and the overall term will go to 0. So this goes to 0 and this goes to 0, and you're left with this evaluating to a. Okay, so what was a? we set A up here, way back here, to be square root of mg over k, which is exactly what we want to match our terminal velocity that we solved for before. So here's the velocity as a function of time as our actual result, and here's a nice little terminal velocity check that when the force is balanced, we do in fact get terminal velocity as matched by a simple Newton's second law approach with zero net force, and so therefore zero acceleration. All right, so that's this problem analyzed in 3 different ways: no drag, linear drag, and quadratic drag, each appropriate for different assumptions.